Okay, so is it live?
It's connecting. Okay, we're live.
Okay, welcome everybody. So we are gathered today for the PhD defense of Hicham Janati. So we start with your talk, which will be around 45 minutes. So I leave you, you can speak.
Anton, maybe can you introduce the jury?
Oh, okay, you prefer, okay, I was thinking of doing it after, but okay. So the jury is composed of, let's see, 8 members. So first, the two referees, Stéphane Heufe from Université de Médecine Berlin, then Filippo Sant'Ambrogio from Université Lyon. Then the PhD advisors are Marco Couturi from NSAE and Google, and Alexandre Blanfort from INRIA. Then the examiners are Klaus Robert from TU Berlin, and Dirk Lorenz from Braunschweig. And finally, Julie Delon from Université de Paris, I think. I'm not sure about the name of the university. And finally, I'm myself, Quentin Rigaud, from Université Paris-Saclay. So after I present the jury, you can start. So you have about 45 minutes. So that's all right.
Thank you. I'll try now to share my screen. Okay, so first of all, thank you to the members of the jury for reviewing my manuscript, for reading it, and for accepting to take part of this committee. My name is Hicham Janati, and I'll be presenting the work that I've conducted during my PhD under the supervision of Alexandre Blanfort and Marco Couturi at INRIA-Saclay. And my research topic is advances in optimal transport and applications to neuroscience. So to start, let's do a small title breakdown, and let me provide you sort of a roadmap to what to expect from this presentation. So the first keywords in the title are optimal transport, which is a theory for comparing probability measures and averaging them based on some notion of geometry. And the second keyword is neuroscience. And in our lab at Varietal, we are mainly interested in functional brain imaging, meaning that we're not interested in the brain anatomy itself, but more at the regions where the brains are active. And we want to do this at a population level. And the first challenge that comes with population level brain imaging is that brains are different. So we cannot assume that different individuals will have brain regions that are active at exactly the same locations. And our answer to that problem is to model or view these brain patterns that you're seeing animated on the screen as distributions or measures, so that we can use optimal transport to model that spatial variability across objects. And the model that we proposed does exactly that. So modeling spatial variability, and you can see the relevant publications below. Now, as you may imagine from this animated image, brain imaging data varies both in space and time across individuals. So we cannot assume that individuals in their brain imaging data, there will be some lags. They cannot be synced. So we need to treat both spatial and temporal variability at the same time. Optimal transport is not enough to deal with temporal variability, so we combine it with another method in time series methods known as dynamic time warping. So we combine optimal transport with a dynamic time warping to create a loss function that can deal both with spatial and temporal variability. Now, in both these challenges, we have large amounts of data. And using optimal transport does not scale very well with large amounts of data. So in practice, we use a computationally computationally friendlier version of optimal transport known as entropic optimal transport. Optimal transport, when regularized with entropy, gains a lot in speed. So major computational benefits, but at the expense of maybe a bit too much blurring due to entropy regularization. So to tackle that blurring, we propose a new algorithm that we keep entropy to get to keep the speed that we want, and but we have sharper entropic averages of brain imaging data. Now, ideally, we would like to quantify how well we did with that algorithm, how well our sharpening method works. And the problem with theoretical findings in entropic OT is that there are no test cases to actually quantify how well we did. So we set out to tackle that challenge by studying entropic OT for Gaussian distributions. And we provided new closed form solutions for entropic OT on Gaussians and studied the barycenters of Gaussians. So this is sort of a large view of my PhD. I'll start with a small introduction to brain imaging data and optimal transport. Then I'll move on to my contributions to neuroscience. And finally, I'll close with my contributions to optimal transport. So first, what is brain imaging data? Let's just forget about time and take one brain pattern, so one brain activation pattern, and we zoom in inside the brain. We get to see that the anatomy is just computationally a set of points, so a point cloud, and that the intensity, the brain pattern, is just a set of weights attributed to each point. So the geometrical component of brain imaging data resides in the link between these points, mainly a graph or a triangulated mesh that represents the surface of the brain. And now you get to see that the brain pattern can be seen as a distribution or a measure defined on the geometry of that brain. And ideally, we'd like to use this geometrical component in our advantage to compare different brain imaging data from different individuals. So let's see what these brain imaging data, what they are from a physiological point of view. So when a brain region is active, an electrical current goes through a certain group of neurons at that location. And that electrical current will create a magnetic field that goes outside the head. So we can pick up that magnetic field by placing a set of magnetic sensors around the head. And the data collected by those magnetic sensors will be are known as magneto-encephalography data, or MEG. So these are time series that measure the magnetic field at multiple locations around the head. Now we want to know where the brain is active. So we need to go back from MEG data back to the electrical current, estimating both its position and its amplitude. Let's fix time for the sake of simplicity. So we take one time point in the MEG data and we try to go back. This problem is an inverse problem known as source localization. Formally, if I model my MEG data with vector y that has n sensors, so n magnetic field measurements, the sources vector, the unknown theta, by vector in RP, then the relationship between the two is a linear inverse problem linked through this matrix n times p that is given by Maxwell equation. So x is known. Now, the problem with this inverse problem, even though it's linear, we can only put so many magnetic sensors around the head, meaning that n is usually, well, always very small compared to p. So we have an ill-conditioned inverse problem, and we need to solve it, we need to add some form of regularization. So this source localization problem was tackled by several communities since the 90s, ranging from Bayesian learning methods to Tikhonov type regularization to deep learning more recently. And the approach that we have set out to follow in my PhD is slightly different. So let's take a step back and see how the brain imaging data, the MEG data, are collected in the first place. So how do we acquire the data? Usually, we invite a subject with an MEG element on, and we have some cognitive stimulus. So mainly, let's say a screen where visual stimulus is displayed of faces and scrambled faces. We collect the MEG data, and now we want to infer where the brain is active. So here, mainly we would be interested in identifying the brain regions that are responsible for facial recognition. In practice, we do this not just for me, but for many other subjects with the same cognitive experiment. So we collect the data, we try to solve the inverse problem, and and we do this independently across subjects. And the idea here is, why not leverage the fact that we have so much data of so many individuals? Let's combine that data. Let's stack it in order to improve the conditioning of the inverse problem. So if I assume that the stimulus, the cognitive experiment, is simple enough so that only a few brain regions are active, I can assume that the thetas are sparse, and that since the same cognitive experiment will most likely induce similar brain regions that are active but not exactly the same, I can assume that the thetas will be somewhat close geometrically on the surface of the brain. So formally, I have a set of inverse problems with some prior information, mainly that the thetas are sparse and geometrically close. And to solve this problem, I can minimize a data fitting term plus a sparse penalty, a sparsity penalty, and some function g that will promote that geometrical proximity across the subjects. So now how we define g? Well, it turns out that, as I mentioned earlier, optimum transport is an excellent tool for modeling geometrical differences between measures. And we believe that this geometrical tool was not fully exploited to its potential by the neuroscience community. So this is our contribution. So let's see first what optimal transport is. So let's take two discrete probability measures, alpha and beta, and we want to match alpha to beta. We want to transport the volume distribution of alpha to beta. And we want to do this by minimizing some form of transportation cost. So it is logical to define this transportation cost as a cost that is proportional to the distance that we're going to travel. So let's measure all the pairwise distances between all these positions, and we store them in a pairwise distance matrix C. Now, what we want to do is to infer to know how much are we going to transport from one location to the next. And we want to infer the exact quantity for all the paths on the screen. So we can similarly model these unknowns in a matrix pi, known as the transportation plan. Now, because we want to transport all of alpha to all of beta, we need some constraints on the transport plan pi. So if I sum the columns of my transport plan pi, that sum must match the source distribution alpha, and if I sum the rows of that distribution of pi, I must find the distribution beta. So formally, it corresponds to pi becomes a 2D distribution, a 2D table, discrete table that has marginals alpha and beta. We want to minimize the transportation cost, so we can assume that this transportation cost, we can define it as the sum of the total transported masses times the distances traveled, and we'll minimize this quantity with respect to pi, and that's the optimal transport distance between alpha and beta. Now we can write this in a matrix form with a scalar product, and now we have a linear programming problem that has a supercubic complexity, which we cannot afford in our applications. So we need to regularize this problem somehow. And one of the most interesting regularization for optimum transport is entropic OT. So adding this entropic penalty to the linear program leads to a strongly convex problem that can be solved using Sinkorn's algorithm, mainly iterations that only involve matrix vector products, and so massively scalable on GPUs. Now, we need to keep in mind that we want to use OT for brain imaging data. And it turns out that even this formulation has a major limitation, which resides in this constraint set. So this constraint set assumes that the mass of alpha and the mass of beta will always be equal to each other, meaning that for brain imaging data, different subjects must have the same global activation intensity, which is obviously not realistic. So we need to relax this assumption. And to do so, we're going to use another variant of optimal transport known as unbalanced optimal transport. Mainly remove the constraint the marginal constraint and replace them with a more flexible penalty between the marginals and the table. Interestingly, even this problem can be solved using Sinkhorn's algorithm. So a modified version of Sinkhorn's algorithm, where the only difference is these constant powers in the iterations. So all operations here are performed element-wise. Okay, so that's unbalanced OT. Now let's see how we can average probability distributions instead of just comparing them. So if I take a list of discrete distributions alpha 1 through alpha a, I want to average them. The most perhaps intuitive idea is to average them using Euclidean mean, so minimizing the variance. To have more flexibility, I can assign different weights to my distributions and have a weighted Euclidean mean. Let's take an example. Two distributions, and I'm going to visualize the barycenter by varying the weights. So the barycenter would vary vertically like this. Using the same idea, I can replace the L2 cost with an entropic OT cost to minimize sort of a spatial variance. And let's do the same thing, vary the weights, and the barycenter will take into account the geometrical component, basically the geometry on the real line, to move horizontally between the distributions. And yet again, even this problem can be solved using a variant of Sinkhorn's algorithm. And this method is also can be also generalized to unbalanced entropic OT with another modified Sinkhorn's algorithm as well. Okay, so now let's take a step back and focus on the application at hand. So if I wanted to describe a usual pipeline in MEG source localization, it would be like this. So we collect the data for different subjects. We try to solve the inverse problem independently across subjects. And then because we are interested in population imaging, we would average these inverse solutions, typically using Euclidean mean. And you can already see here that the Euclidean mean, because of spatial variability across subjects, will lead to something that is very much blurred. And so we lose the fine grained detail of regions of interest in the brain. A first step to improve on this pipeline was proposed by Gonfa and colleagues a few years ago, and basically they replaced the Euclidean mean with an optimal transport barycenter. And you can already see the massive reduction in spatial variance when using optimal transport. Now, perhaps the limitation of that work is that first, the optimal transport barycenter only intervenes at last, after all the pipeline is conducted. And the second criticism is that well, they modeled brain imaging data as algebraic vectors, not as measures defined on a geometry. So we want to remove these normalization tricks that generalize the use of optimal transport and use more adaptive technique, mainly that we've discussed earlier, unbalanced OT. So we want to get rid of the independence across subject and use a more principled tool from the OT theory that is adapted to signed measures, given that the brain sources are signed vectors, so electrical current amplitudes. And second, we want to get rid of this independence when averaging across time. So that's where our contribution, where we combine OT and dynamic time warping, comes in. So with this, I can move on to my second section. So first, I will present the first contribution, and then the second, which will be the subject of the second part of this presentation. So multi-subject source localization. Let's go back to our original loss function. So I want to minimize some geometrical variance. When we say minimize variance, we immediately think minimize this Euclidean variance on the screen. So that by replacing the L2 cost in that variance, we can, as I mentioned earlier, replace it with optimal transport to have a more geometrical component in that variance. So here, replacing this function g in the loss function, you can already see that when I will minimize with respect to theta bar will correspond to a barycenter of my subjects. So alternating between theta and theta bar will lead to an alternative algorithm where I am solving the inverse problem for each subject, and then I'm computing a geometrical barycenter, and then forcing the subjects to not deviate too much from their average, from their geometrical average. And so here first, because UOT is defined only for positive vectors, so this is what the algorithm would look like if we had a positive t constraint. First, minimize each theta t with proximal gradient descent, and then update theta bar with Sinkorn's algorithm. Okay, now we know how to solve this problem for positive measures. We can generalize it to signed vectors by basically writing each theta as a difference of positive parts, positive and negative parts. And we double the number of variables, so we have a barycenter for positive parts and another barycenter for negative parts. And that's what we call MTW for multitask Wasserstein. So that's our model. Let's see some the results, the performance of that model on some simulated data. So here we simulated data for 32 subjects. Each color on the left, each color corresponds to a subject, and we have some degree of overlap across subjects. So we compare the performance in source reconstruction by computing EMD for Earth mover distance, which is just the optimal transport distance normalized after projecting all the vectors onto the simplex, onto the probability simplex. And you can already see here that the best performing models are MTW and MWE, which are both models that we proposed based on OT barycenters. And MWE is here just a variant compared to MTW, and that I will be happy to discuss with you later if you want. So the other models here, you can see that the lasso is and does not increase in performance, which is normal. And the other three models are block sparse models, basically improved versions of the group lasso estimator. And you can see that after a certain number of subjects, their performance is saturated. Now let's move on to some real data experiments. So here I'm going to show you the effect of the geometrical regularization by increasing the hyperparameter mu of our model. So this is the CAMCAN data set. We took 32 subjects of the data, and we are going to increase mu. So here each color is a subject, and when we increase mu, we force all the subjects somehow to have a consensus around the auditory cortex, which was expected here since the stimulus was an auditory evoked response. So all the methods that I've mentioned earlier, the benchmarks and our model, are implemented in this Python package, mutar, for multitask regression in Python. It follows this, and it follows the scikit-learn API. So here you'll find group lasso implementations and its variants and our MTW model. And second, more brain imaging-oriented package, group MNE, for multi-subject source localization, which follows the MNE Python API. So this concludes my first contribution in neuroscience. Let's move on to the second one. So I have brain imaging data that varies both in space and time, and I want now to combine optimal transport with something that will capture temporal variability. So first, to make things simple, let's just have two time series and forget about brains. So I have two time series, and I want to find an alignment that respects the chronological order of the data and that captures temporal shifts. Let's represent that alignment with a binary matrix A. And to make sure that I respect the chronology, if I am at this current state, I cannot make this alignment. So I cannot go back in time, which formally means in my alignment matrix A that I can only go down, go right, or go down right. And this constraint leads to the set of alignments that look like this. So they go from the top left corner to the bottom right corner. And this set is known as the Delanois set. Its size is known as the Delanois number or Delanois double sequence. Now, the question that we are interested in here is, what is the best alignment A? So let's assume that aligning I with J costs me some delta between xi and yj. I minimize this quantity with respect to the set of Delanois alignments A. And then I have the dynamic time warp indices, which was proposed in the early 70s. This DTW can be computed using dynamic programming algorithms. Now let's write it in a more convenient matrix form. And let's visualize that pairwise distance matrix delta. In the current example, you can see that the blue time series is shifted with respect to the red one. So here in my delta, I can find this alignment which does not touch delta and will have a zero alignment cost along the way. So DTW here is equal to 0. If I move one time series with respect to the other, I can still find another alignment with 0 cost, which means that DTW cannot capture temporal shift regardless of the size of that temporal shift. So we need to find another variant of DTW that does that. If we replace the min with the soft min, which was introduced by Couture and Blondin for differentiability reasons, then we can actually start to capture that temporal shift. And that is basically my contribution to a dynamic time warping. So if I write the definition of the soft min with the log sum x, in this sum, I can isolate the exponential terms that are equal to 1, basically the terms that lead to 0 cost. And those terms will lead to this Delanois number of the set of alignments that lead to 0 cost. And so here you can already see that the Delanois numbers will change when you shift one time series to the other, because the set of alignments that lead to 0 cost change. And by doing some combinatorics, we can prove actually that the soft DTW increases quadratically with temporal shifts. So if beta is small enough, then we have this quadratic lower bound. So in purple, you have the empirical computation of soft DTW, and in yellow, the theoretical bound that we proved. Now, the idea of the proof is fairly technical, but to get you to give you a sort of an intuition, let's just see what is the main technical contribution in this to prove that theorem. So this is the Delanois double sequence, and what we already know in the literature is mainly the diagonal. So the diagonal sequence is the most studied Delanois sequence, and we already know some relationships between these Delanois numbers. Basically, here an arrow represents lower than. So we already knew this inequality. But to prove my theorem, I needed to compare all possible elements in this table. So we set out to do exactly that, and we proved these tight inequalities that depend on both the position and the transition shift. Okay, so now we have a spatial temporal loss. Let's test it on some simulated data. So here, how am I going to define it? Well, basically, I have soft DTW that captures temporal shifts, and I have OT that captures spatial shifts. I can just plug in unbalanced OT as a cost function in soft DTW to align time points that are spatially close to each other. And now let's simulate a set of brain imaging time series that have, if you focus on the legend below, you have 2 time points for the brain activation and 2 zones, which are brain regions. And now I'm going to increase beta sort of to move from DTW to soft dynamic time warping. To its soft version, so as to capture more temporal shift. And you can already see here that by increasing beta, we start to separate the colors, which are time indices. So our spatial temporal loss works very well for spatial temporal variability. But our real objective is to average brain sources both in space and time. So if I have multiple brain imaging time series, I want to average them. How should I do that? similarly, we can, as we did before with OT, we can define the Fréchet mean of that loss function. And a straightforward solution to that problem would be to say, well, this is differentiable. Let's just do a chain rule, and we would have these gradients to compute. Now, the first gradient, the first gradient can be computed with Sinkhorn's algorithm. The second gradient can be computed by backpropagating the dynamic programming algorithm. Now, the problem with this approach is that the first gradient, the gradient of UOT with respect to the time series, UOT here is a distance matrix. So it's a pairwise matrix that contains a lot of UOT values. So we need to differentiate t square UOT variables just to compute one gradient of our major barycentric loss function, which is pretty much impossible to do in practice. Instead, we took a different approach. So if I write the definition using the log sum x, I can already see that what bothers me in this expression is that the UOT terms are inside the log sum x, because I already know how to compute large linear sums, minimization sums of UOT using Sinkhorn's barycentric algorithm. So the idea is, let's try to take UOT outside of the log sum x. And to do that, we can use functional duality. So the log sum x is the functional conjugate of entropy. And by doing this, well, we can get out the UT outside of the log sum x, and we have now a linear term that we can minimize with Sinkhorn. But not so fast, because here the log sum x is a sum over all possible alignments, which means that the argument that follows from functional duality will have an exponential dimension, which is the Delanois number. So we do not want to compute the thetas. And actually, we don't need to compute the thetas, because to update my barycenter y in blue, I only need to know this highlighted matrix in green. So I only need to know this sum, which can be seen as a form of average alignment. And it turns out that this average alignment corresponds exactly to the gradient of SDTW with respect to the UOT matrix. And we already know how to compute that using backpropagation. So our algorithm would look something like this. First, compute the average alignment A bar using backpropagation, and then compute update the barycenter using Sinkhorn. And so here you can already see some spatio-temporal intuition, where the A bar is an alignment matrix, an average alignment, and it contains all the temporal information, temporal weights that will be given to the Sinkhorn algorithm to average, to pick from all time points and average them. Let's see an example. So here we have the averages of real brain imaging sources from the S117 dataset, basically faces stimulus. And if I compute in this experiment, well, first I expect two evoked responses. The first one around 100 milliseconds for the visual response, and the second one around 170 milliseconds, which is specific for recognizing faces. So this is the Euclidean mean across 16 subjects, and you can already see that we have the first reaction around 100 milliseconds and the second one around 170. But we have a bit too much spatial variability across subjects. If I compute the barycenter only on space, so just independently across time, I lose the first reaction at 100 milliseconds. When I use my own loss function STA, spatio-temporal mean, now I recover the first one, and I still have a good spatial resolution. And to get a clear picture of the temporal benefits of this loss function, let's remove a space from the equation. So compute the L2 norm across space, and just see the L2 norm across time of my brain sources. So here you can see that the spatial-temporal loss, the spatial-temporal barycenter, has more distinct this double peak in its time course. So it identifies more precisely the both evoked responses. Now, I have what I've said so far corresponds to this loss function. Basically, use optimal transport as a cost inside DTW. But to be actually fair, well, we did not actually use entropic OT directly, because entropic OT suffers from entropic bias, which basically corresponds to this identity here that entropic OT is not 0 when x equals x. So we actually used a modified version of UOT, and which will be the subject of my last section. So let's move on now to my contributions to optimal transport. So first, what is entropic bias? From a theoretical perspective, OT is not positive, and it is not minimized when the measures are equal to each other. And when used as a loss function in machine learning, well, we have this annoying property that it is not minimized when we fix one measure, so it cannot really be used as a loss function. From a more practical perspective, let's when we compute barycenters of images, for instance, entropic OT will recover the good shape that we expect, the common shape across images, but it will be massively blurred. Several attempts to fix this have been proposed in the literature, and perhaps the one that stands out is the Synchron divergence, which consists in basically just removing these autocorrelation terms, alpha, alpha, and beta, beta, beta. And theoretically, it has good properties. So now we have a non-negative function, and that is minimized when alpha equals beta and the loss equals 0. Good. So that's so some good progress from the theoretical perspective. What about barycenters? What about, can we compute barycenter using S? And it turns out that we can, by simply just noticing that this is convex and differentiable, and just by canceling its gradient, we can obtain an algorithm that is very similar to Synchron's algorithm, where the only differences are the ones highlighted. And in practice, so the best case scenario would be to have a visual barycenter that looks like the one on the right, which corresponds to no regularization at all, but it is too slow to compute. And using the algorithm that we proposed on the right, we can actually have a very similar barycenter to the non-regularized one in a much faster computation time. This implementation of this algorithm will soon be available in a NumPy and PyTorch implementation in the bot Python package, and in a JAX using JAX on the OTT toolbox. So the approach that I described here can also be adapted to debiased or unbalanced barycenters as well, give or take some minor subtle differences from the theoretical perspective. So we have seen that in numerical experiments, this algorithm performs very well. We could debias, remove the effect of entropy, or almost. What can we say now about this debiasing from a theoretical perspective? Well, to answer that question, we are going to study entropic OT for Gaussian distributions. So in the continuous setting, we are going to focus on a quadratic cost, and we are now looking for a distribution pi that has marginals alpha and beta. And if we assume that alpha and beta are Gaussian distributions, then we already know since the 70s that we have this closed form that depends only on the means and variances of the Gaussians, known as the Bjorn-Wasserstein metric. So what about entropic OT and unbalanced entropic OT? Well, for entropic OT, we did the exact same thing. So we showed that we can solve Synchron's optimality condition in closed form, and we obtained this loss function, this closed form that is very similar to the Bjorn metric, with an additional log that term here and the modified trace term in the C vector here, matrix here. Similarly, for unbalanced OT, we discovered a new closed form as well. So we showed that the unbalanced OT is has a closed form that depends only on the masses of the inputs and the mass of the plan, pi, which is also given in closed form, depending on the parameters of the Gaussians. So in both these theorems, what I forgot to mention is that both pi, the transportation plans, are also Gaussians, and we've identified their parameters as well. Now, with all these new closed forms, we can go back to our barycenter problem and evaluate how well we did in our debiasing. So if I take a sequence of Gaussian measures, and I try to compute their barycenter with S, with the debiased loss, then I can prove that if I minimize this loss on the set of sub-Gaussian measures, then the barycenter will also be Gaussian. Its mean will be equal to the mean of the means of the Gaussians, and its covariance will verify this fixed point equation. And here in particular, if you assume that all sigmas are equal to each other, then the solution sigma will be equal to all the other sigmas. So we've achieved real debiasing for Gaussians if they have the same variance. Now, the proof of all these three theorems remains on a very small observation, which is that if you look closely at the synchrone equations, so here I have both balance and unbalance, you can see that they are very similar except a multiplicative term. So I can focus on the balanced one. And if I assume that alpha and beta are Gaussian distributions, then the densities will be written in this form, so exponentials of quadratic forms. And usually in Synchron's algorithm, we start with by initializing the potentials f and g to 0. So if in this algorithm I initialize g with 0, then I will have basically an integral of an exponential of a quadratic form, which I can compute in closed form. And this simple idea leads to the fact that, well, we can prove that Synchron's algorithm actually by starting from 0, the potentials f and g will always remain quadratic. So if we assume that f and g are quadratic, written in this form, then Synchron becomes a matrix problem, a matrix fixed point matrix problem. And by doing some linear algebra and some change of variables, we could solve this system in closed form. And perhaps if I had to highlight one technical trick that was extensively used in these technical derivations, it would be the Woodbury identity, where the way I see it is just an equivalent of what you would do in the real line when you add and subtract terms. So whenever you have inverses of sum of inverses, think Woodbury's identity. It can be very, very useful. So that pretty much sums up my contributions to optimal transport. So where do we go from here? Well, if we stay on optimal transport, we could push further. We could try to find new entropic OT closed forms. And one thing that we noticed when we found the closed form of the unbalanced case, we could let the entropy parameter go to 0, and we found a new closed form without entropy for unbalanced Gaussians. Perhaps we can do the same thing for other formulations of optimal transport and let entropy pave the way to discover new theoretical findings in optimal transport. Well, about neuroscience and brain imaging, well, we're not quite done there yet. We still haven't solved the spatial-temporal inverse problem yet. We've solved it in space, but not in space and time. And first, before we do that, we need first to try to scale to hundreds of subjects. For now, we have solved the inverse problem for 32 subjects. That takes around 5 minutes to solve. But brain imaging data nowadays are available for hundreds of subjects. So we need to scale our algorithm to hundreds of subjects. And that concludes my presentation. I'd like to close by thanking all by my supervisors and all of my co-authors. And thank you for listening.
Okay. Well, thank you, Hicham. So we may switch to the questions. So we start with the referee that is usually in front. So we start with the furthest referee, who will be Stefan Hoife from Berlin.
Okay, thanks a lot for the impressive presentation, which was, I think, no less impressive than the thesis itself. How much time do I have?
Typically, let's say 5 to 10 minutes per person, things like that.
Okay, so
it can be more if you want. So.
So I mean, I have a few very simple technical questions also related to understanding, but also a few more high-level questions. So let me start. So basically, what my first question is: why is the entropic regularization so prevalent, and could there be other ways to speed up the problem? And in particular, what I noticed is that the optimal plan, it always seems to be a line, right, in this space. So could there not be a way to enforce this structure, that you do not have these like broad transport plans, but thin lines? And also, could there be ways to maybe adaptively go from the regularized solution to the unregularized solution by thinning or by initializing the problem?
Yeah, that's a good question. There are many directions in that, basically, even in entropic OT, such as multi-scale solutions, where you would start with a large epsilon and start and just go down with your epsilon. It works very well in practice when you want to compute, for instance, barycenters. It's very fast and it gives good results. But we have no theoretical guarantees that we actually converge to the right barycenter. Other regularization of optimal transport exist, and for instance, if you remove entropy, that causes, well, with entropy you wouldn't have a line, you would have a blurred line. There are other regularizations with L2, for instance, that lead to more sparse transportation plans. But the way I see it is the main benefit of entropic OT is that it gets rid of the positivity constraint on the transportation plan with the x log x penalty. And that's not the case when you use L2. So when you use L2, the dual problem would still have a positivity constraint, and you would not be able to decouple the dual variables. So that, I believe, is a main reason why entropic OT leads to a very fast algorithm.
And regarding the applications in neuroimaging, so basically we have vector fields there, and what you already used the simplification that you have signed quantities, so you fix the orientation, and then you do this OT separately on the positive and negative parts. And I was wondering whether this is whether there could whether strange things could occur, like for example, when you do this when you compute the barycenter. Wouldn't it be possible that that the barycenter actually has a positive and a negative component at the same location? And what does it mean?
Yeah, yeah, that's a good question. From a theoretical perspective, we have no guarantee that there will never be an overlap in the sign. You would have guarantees if you would only use the sparsity penalty. Basically, because you write theta as a difference of positive and negative parts, and the L1 we could always decrease the L1 if you have overlap between the signs. But for optimal transport, that's a bit more tricky to prove, I believe. But in practice, we throughout the algorithm, when I observe throughout its convergence, I never observe any overlap across. Perhaps that's mainly due to the fact that the sources are sparse, and that decreases the chance of having a massive overlap between the two.
I see. And would there be a straightforward extension to vectorial quantities, or would that be too much?
That's a good remark. But well, I actually reviewed a paper recently that tries to do something similar. Not in brain imaging, in microscopy something. I forgot the application, but mainly the underlying idea was to use the Benamou-Bonnier formulation of optimal transport, where you would model your images as velocity fields, and they used they solved the differential equations to discretized differential equations to actually estimate their sources as velocity fields. So I think it could be possible to.
And then basically, when you look at brain data, you always have to use this like unbalanced OT. But as far as I understand, there's no, the difference in energy is not penalized in this approach. Should it not also be something that should be penalized? So basically, when one distribution is the scaled version of the other, this wouldn't incur any penalty, right? But shouldn't there be also some term?
There is, yeah.
There
is actually a parameter for the marginal discrepancy.
Okay.
And that's mainly a limitation when you have very large differences between your amplitudes. That's rarely the case when we solve the inverse problem in space, but because usually the subjects would not really differ too much in terms of amplitudes. But it is a problem when you perform spatio-temporal averaging, because then you would need to compare time points where you would have nothing in the brain and time points where you would have massive amplitudes. So then it becomes more important to tune properly.
That actually brings us to chapter 4, and this is actually one thing that I didn't understand. Why is dynamic time warping at all necessary? Couldn't you just have a spatio-temporal OT variant? And doesn't OT already encompass all of dynamic time warping, so it's strictly more powerful? So why this extra method?
Yeah, well, perhaps the easy way to do it would be just to consider time as an additional feature and just penalize it with another cost. But the problem then would be, how do you, well, then you would have an additional parameter for how you would calibrate space and time. Yeah, but the alignment that you would obtain would not necessarily guarantee that you would not, that it would be monotone in your, well, you wouldn't have a line basically going from the top left corner to the top right, to the bottom right corner, because. But
in practice, it would probably always be like that, because the optimal plan is always, you have these like, because it's a minimization.
Yes, but you don't have hard in DTW. You have hard constraints on the beginning and the end of your time series that guarantee that you would go from one time point to from the beginning to the end. And I think maybe unless if you do some form of multi-scale where you would transport first just in space and then try to transport in time, I don't think that you would keep that monotonicity as if you were just doing optimal transport just in time. On the real line, that would work, yes. But in larger dynamics.
Is it so different from the spatial domain? So it's basically in space, it means that you're not guaranteed that you're actually transporting one activity to several locations and in time. But okay, I mean, I don't see the big conceptual problem here, but of course the way you do it is also very nice. Maybe one last more conceptual question is also about neuroscience. So basically, when you do neuroscience, what you usually want to do is you want to present a p-value of. So basically, you're looking at two different cohorts, say, and you want to show that they are different. So the first question is when you do this group-wise regularization, don't you lose the ability to actually do statistics because you have already coupled all these subjects? And the second is actually, how would you, even in the independent case, how would you do statistics? Say you want to prove that this group mean is located here with a certain confidence, or whether the barycenters of two groups differ. and not only in general, but maybe per location. Is there a way to achieve this in this framework?
Yeah, I think once you add the optimal transport, especially with entropic OT, you lose entropic OT is not a distance. You lose several theoretical properties of OT as a tool to compare probability distributions. And I'm not sure you can really have such guarantees, but I thought of it in the beginning when before I actually tested it on real data, and I wanted to keep the appealing properties of OT and just maybe perhaps find a way to include it as a Bayesian prior, so as to keep to have a theoretical framework to do it. But at the end of the day, it was pretty much impossible computationally, and we backed to entropic OT.
Okay, but also conceptually, basically, when you have you are able to say compute a barycenter for a group or for two different groups, but it's not so easy to really say that they are different. Or would there be like, what would be reasonable null hypothesis to test against, like testing against a uniform distribution? So you want to claim that what you measure is actually focused on some area, so you have to do some permutation tests? Or?
Yeah, you have to, yeah.
Okay.
You could resort at the end to non-parametric tests.
Okay. Okay, thanks a lot. So, I mean, I had one more question. On the technical side, it's just out of my own interest. So what if, say, the spaces of two distributions that you want to compare is different in the sense that, let's say, one distribution lives in a subspace of the other. Would these methods still be applicable, or would it kind of break down because, like, let's say you have a 2D image and one distribution is just one is a 2D image that is actually a subspace of a 3D image. Mm-hmm. Is it something that you could still compare with OT?
If you regularize it, yes. You mean in general with OT, or specific to brain imaging, or
in general?
Yeah, you could. Well, from a theoretical perspective, you would need to have some form of regularization either on your measures or on your optimal transport problem. So, for instance, with Gaussians, you can transport if from one to the next, you can always have a transportation plan between the two. But if the support of the smaller one is if you want to do a matching, you would only it would only be possible if the support of one is included in the larger one. So you cannot do the opposite alignment.
Okay.
But when you realize with entropy, it's like you're blurring the entire space, and then you don't have any problems in your support.
I guess from my side, I would like to thank you.
Thank you, Stefan. So we move on to the second referee, so Filippo.
Okay, so thanks, Quentin. So first, I'd like to thank Hicham for his presentation, because, okay, I went into the thesis, but of course, there is a lot of material in the thesis, so it's not easy to fully follow everything. And the presentation was quite clarifying. I don't know if it was also motivated by some questions that I asked, but I found many answers to some general questions that I was wondering. In particular, I thank you for your introduction about the role of geometric proximity on the parameters theta in the very beginning. So I thank for this presentation, which is really a very, very good presentation. So I'd like to add some questions. I also have some questions which are sort of high-level questions on the general philosophy or spirit of the thesis, and some more detailed question. I will not ask a lot because I already made many remarks on the thesis. So the first is about the general idea behind the thesis. So you have a lot of techniques and results about optimal transport, and you apply them to neuroscience. And my question is, why? in the sense, does it come from just the motivation is just that you have questions from neurosciences because the question arises in some applied setting, or because you have data on neuroscience and then you use your techniques from optimal transport and you apply to this as a case study? That is, you develop your techniques in optimal transport and you just check on this very specific question if they give satisfying result, or do you, or does it happen in your thesis that you had to develop or to think something specific to the neuroscience application? Do you have to develop specific models or specific algorithms which fit well the neuroscience, the features that you observe in neuroscience and do not have been the same in other applications? This is a general question that I often have when I see some, let's say, some sort of optimization, and in particular optimal transport method applied to data science. Is it specific to the set of data that you have or not? So this is my first question.
So thank you for your question. Yeah, the PhD started with the multi-subject source localization problem. And the idea was to let's use optimal transport, mainly just apply it to model the spatial variability across subjects. So that was pretty much the first project in the thesis. And then as I moved on, I started digging into more optimal transport and into dynamic time warping. And that led to the spatio-temporal OT. And as I started doing more optimal transport and more theory, I started diving more and liking more optimal transport theory, for that matter, just for out of the curiosity of it. And that's how it led to the study of the entropic bias. And then out of the blue, we just thought, well, we have to quantify that entropic bias. So let's study Gaussians. So first we studied Gaussians just on the univariate case. It was quite very simple. Just all the barycenter theorems were first done just in the univariate case, and then I thought, well, maybe it would be easy to just generalize what's so special about the univariate case. Let's just push it forward and try to see what will happen if we try to solve synchrony in the multivariate case as well. So so the roadmap of the thesis started as an application in neuroscience, and then it started shifting more to optimal transport at the end. But I still care very much about both of brain imaging applications and the theoretical contributions to OT.
Okay, so in some sense, it's by chance that you had to work so deeply in optimal transport because it worked well, but the original motivation was in neuroscience. So I have, in some sense, a similar but more mathematical, less interdisciplinary question about the interaction between two objects, which is in the dynamic warping part. Because as you do, and it also features what Stefan was asking, you treat, so you have a dynamic warping question about how to treat time. In each time, so you have some spatial datum, and it is given your matrix delta of the distances. In your case, it comes from, so it is given, then you will also have to optimize when you try to do a barycenter. But in your case, this distance comes from an optimal transport or a regularized optimal transport distance. But how much of what you do is specific to the optimal transport setting, in the sense that it seems that there is a lot of what you do, in particular about the study about the Delanois numbers, which is not specific at all to this. It's just a combinatorial study about how to do time warping. And but it seemed from in particular from your presentation, more than from your manuscript, I would say, that some tricks based on the fact that in this dynamic warping approach, there is a linear structure in the sum among all possible matrices which correspond to alignment, and using a convex duality, then it matches well with the linear structure or convex structure of the optimal transport cost. So also this was a question: how much of what you do in dynamic warping works well with the specific spatial cost that you use, and how much would not work with other distances?
Yeah. So first, when I started working on dynamic time warping, I started just working on dynamic time warping with the Euclidean cost. And that's when we noticed that when we use the soft minimum, the barycenters, just with the Euclidean cost, start to be in the middle when you compare two time series that are shifted. So that's when we spotted that, well, that was actually done by Marco and Mathieu Blondel before. They proposed an algorithm to compute barycenters of using just the Euclidean cost, and the fact that it led to spatio-temporal sensitivity led us to believe that, well, we could if we just plug in optimum transport there, we could capture spatial variability as well. But I guess your question was on on how well dynamic time warping performs well on itself without OT, or
if you had data which, instead of being let's say measures and the delta matrix being optimal transport cost or regularized optimal transport, if your data was something else with different kind of cost. So you said that you started from the Euclidean distance, so it means that your data were points instead of measures with standard distances, and you could anyway see some similar features. So in some sense, what you do in the case of measures, it's a natural extension of what you do in the case of points in the Euclidean space. That's what you're saying.
Yeah, well, the link between the two is just simply, well, we are identifying the measures with their weights. So basically, then because the geometry is fixed, that's the main difference between. Well, we're not really exploiting optimum transport fully because the geometry of the branes are always fixed. So the supports of the measures are always fixed, and we do not really do any particles do not move. So we're not really exploiting OT to its full potential. And for computational reasons, and because the brain imaging data, because the brains don't move, OT, entropic OT as it is enough.
Actually, my question was more about do you exploit some sort of algebraic structure of your optimization problem in the optimal transport, the fact that you have something linear with some penalization and so on, and in the commutation between the soft mean which arises from the dynamic warping and the minimization over pairings over transport plans that you have in the spatial part.
You mean the linear part? You mean the linear in the optimal transport linear cost linear?
Yes, but also in the dynamic warping, since you're doing a soft mean, you're minimizing some average in some sense. Okay, but and you're exploiting the fact that you had an exponential and a logarithm, but you get rid of them using a convex duality.
Yeah.
So it seems that the linearity plays an important role.
Yeah, certainly, yeah.
Linear structure. Now, I would like to pass, probably it's the last question, to something a little bit more technical. So on this, in particular in this specific setting, you explained that you need some, no, maybe it was not only in this, but you need some proximity. You want to consider barycenters, but sometimes you don't have positive measures, and so you separate positive and negative parts. Stefan also asked this question. By the way, I agree with him. It's in general, if you have two measures with positive and negative parts, or more than two, and you take the barycenters, what you get, you have positive and negative part which overlaps. And the answer that you gave about the fact that sparsity could help, so in some sense I agree, but not so much, in the sense that first, when you have this barycentric cost as a proximity cost, your theta bar is just an extra variable which is not penalized in the sparsity. You're not penalizing the L1 norm of theta bar, you're penalizing the norm of the theta. So there is no reason in the minimization to prevent theta bar to have useless positive and negative part overlapping.
I agree.
What probably happens because of the sparsity is that if the theta are very sparse, it's very unlikely that they align in a way such that the barycenter could overlap. Because if you were in 1D, you take a measure with positive mass on 2 and negative mass in 1, and the other positive measure in -2 and negative mass in -1, the barycenter has two masses which compensate in 0. And if you do a barycenter with a parameter, instead of a weight, you really see some positive and negative mass which move. At the moment, they compensate just when you have the parameter which is 1/2, and then they move. So in general, it's possible. So this in some sense says that maybe when you treat positive and negative measures, it's quite arbitrary to choose to separate the positive and negative parts, even if I don't have any better solution. My question is, did you try, for instance, if you have bounded data, just to add the constant to everything so that you transform everything into positive part? Of course, it's not the same. We know in Wasserstein 2 cost, the distance between a measure and another and the distance between the same two measures plus a constant is not the same. In Wasserstein 1, it's the same. In Wasserstein 2, it's not. But anyway, since you do an arbitrary choice in separating positive and negative part, what could happen if you just decide that, okay, you have some theta which could be positive and negative, but they never go below a certain, I don't know, minus 100 value, and you just add the 100 to everything, and you do standard barycenters just with the positive part. Did you try? Do you have an idea about this?
Yes. So first, for when you separate negative and positive parts, I tried to find the least sufficient condition that I could add to the problem to guarantee that, because if from a theoretical perspective, you can argue that the barycenter of the positive parts will be included in the convex hull of your inputs, and similarly for the negative parts, and there is no reason for those two convex hulls not to overlap. So basically, you could have any overlap, but because the number of sources are too small, there is, well, in our experiments, we didn't observe that out of chance. But yeah, the first thing before doing the sign splitting, we tried to just minimize the optimal transport between the square of the measures. Or the absolute value, but that leads to numerical problems with differentiability around 0. And also when you square, you get an amplitude bias, because then if like the source estimates have low amplitudes, then you need to compensate that bias somehow. And we just gave up on that, and we picked perhaps the easy solution.
Okay, so you tried other solution, but in practice, this is the one which worked better among what you tried. Okay, it's okay from me. I will stop here. Thanks, Kenta.
Thank you, Filippo. So now we move on to the examiners. So let's start with Klaus Robert from Berlin.
Okay, yeah, so very impressive. You know, both the thesis and also the presentation. I was chatting with Marco about trying to lure you to Berlin, but since this is live, you know, I still think this is a good idea. But anyway, so, well, there's a lot of things that one can ask, and some of the questions were asked by Stefan and Filippo already. But some of them have also made me think about my questions, and one, which is a very simple one, which comes right next to Stefan's question about the subspaces. If you want to compare the, you know, one space and the other one is more like a subspace thereof, then, you know, having this in mind, I wondered, and you know, I always wanted to ask this question to somebody who knows optimal transport. How about, you know, if you think about, you know, neuroimaging data, it may well happen that some of the sensors have different, systematically different noise levels, right? So it could be, you know, this could be, you know, generally true for some sensors, but it could also be true for some subjects, for some specific sensors. And I would like to understand, you know, in the same sense that Stefan asked, what would happen in such a scenario?
So you're trying to match a smaller group of sensors from an individual to a larger one?
No. You say you have different measurements,
yeah,
and let's say for the simplicity, this is really the same subjects, right? Mm-hmm. Sorry, it's the same instrument. But sometimes, you know, this instrument has a bad day, or the subjects are not very well aligned, and you know there are some systematic issues with the sensor readings and some some sensors are more noisy. Okay, so that's
yeah. So we're still in sensor space.
Yes.
And you have some bad sensors, and you want to complete your data, sort of do some interpolation based using entropic OT and complete the data using the other subjects.
Whatever. I mean, I think that if you would have this different noise, then the data is not really living in the same distribution, isn't it?
Yes, but I'm thinking from an MEG perspective, where you would you basically have time series, and I'm not sure how you could, because when you were working with your MEG data, you cannot just consider that they're just sources. Well, I mean, the time frequency aspect of the data, I don't think it will be preserved if you use optimal transport to just ignore the frequential part of it and just align subjects.
I understand. I mean, I understand that you're aligning in source space.
Yeah.
But still, if you would have these problems in the sensor noise, this would probably do something with the source space. I mean, would it be as accurate, or it's so to say an issue in the data that will reflect itself in the properties of the source space, and that will then later on reflect of what optimal transport needs to do. So my question is a bit looking at the whole thing.
I mean, I don't believe that you would use optimal transport just to predict sensor data, but you could use optimal transport to just perform the alignment, like to just identify what sensors you would use from other subjects to do your interpolation, for example, or things like that. Use the data just to infer, for instance, the positions, or something more high level than just measuring the amplitudes of your MEG measurements.
Right. Okay. So, so if we, let's for the moment think that you've done that, but the noise will also make your source space estimation less accurate. So for some subjects, this estimate will be less accurate than for others. So what, if you want to then do any statistics over the subjects, and if you would like to do your optimal transport, then what will happen?
So if you have outliers, basically, your variance, you'd need a lot of subjects to compensate to be robust. But in practice, yes, if you have outliers, or optimal transport, barycenter can be skewed towards that outlier if it has a significant amplitude. So that's a problem if, for example, in the inverse problem, you combine data that are not similar. So that's truly a limitation in our work, which is that we assume that subjects are similar, and we do not try to quantify that similarity beforehand. So one thing we could do is maybe learn first which subjects are more similar to each other, do more of like learn a graph of similarity, and then adapt weights. Sort of to have low weights for the noisy subjects and the ones that are very different from the rest.
Yes.
But using optimal transport alone, that you would have bad results due to noisy subjects.
Yes. Okay. So then I'm fully agreeing with everything that you said, right? I think in MEG it's less pronounced the problem, but if you would have EG, it's just hell, because your sensors get loose all the time, while you have fed all sorts of issues, right? So therefore, okay. So then one thing is, of course, and that comes again, it's still in the same realm. So you go to source space, you make your estimate to get there, and then you do your optimal transport. So isn't it some, it's like a two-step process. So how can you make sure that in the two-step process you're not collecting all the errors along the way? So is there a way you could?
Well, we alternate between the two steps before we get to a final solution. So the
Yes.
problem, it's a nested loop where you would compute the average and then force the subjects to be close to that average until you converge. But if
just to say, I mean, some subjects are good subjects and they are actually doing what you're telling them to do, and some subjects are just doing something, sleeping, whatever. So I mean, how can you? I mean, it's in a sense a very related question to before. I mean, that's not the noise by the sensors, but it's so to say the noise that the brains generate if the subjects are not, if you're sleeping or doing something. So how would that reflect?
So again, you would need large, well, I mean, if half of your subjects are not doing what they're supposed to do, then you have a big problem if you are forcing everybody to agree on something.
I mean, it's clear to me that in Germany and in France, people would, rarely agree on anything. But in the case of these experiments, it's quite common that just take me as a subject, I'll be sound asleep after 3 minutes. It's, and if you have children, it's perhaps even quicker, right? Do you have means, or do you have? I mean, of course, you could try to get rid of these subjects, or
So in all our experiments, we actually we did do that. We for instance, with the Can data set, I picked the 32 subjects that are all younger than 40 years old or something like that, I guess, or maybe just to have a sort of an agreement in their auditory response, basically. And we performed independent source inverse solutions. We looked at the solutions, and there were some subjects that not in the auditory response, but more in the visual response, that you couldn't see any activation in the occipital lobe, and it was all like a default mode network. So we eliminated those subjects.
Okay.
And we kept the subjects that had basically, just by looking at the image data in sensor space, you would just look for subjects that have the spike at N100, and then you would keep those.
Okay, so I think this is a very good strategy. So coming back to Filippo's question, which I liked, it's like my brief summary would be, why did you look at the neuroscience data? Was it just on your hard disk? I mean, something like that. So having asking this question slightly different, is did you actually get any interesting new insights from the neuroscience perspective? Because you now have some really sophisticated and extremely interesting mathematical tool with which you can analyze and which you can use to understand more about doing statistics over these subjects. But then the question is then, now what? So what do you have, right?
Yeah, that's an important question, because right now, I've been building models to solve the inverse problem for multiple subjects. We made that model sophisticated enough, but at the same time, we are increasing the complexity. and we have the sparse penalty, the optimal transport penalty. Now DTW will come to. We have non-convex regularizers. So there, the concomitant estimation where we estimate the noise. So we have lots of tools combined, and I think that now is the moment where we should take a step back and maybe see what other people are doing. And mainly, I don't pretend that my model will be the ultimatum to solve the inverse problem. And I think as a community, we need to more focus on sharing public data, organizing more data challenges so that we can...
I'm agreeing with all that, right? And yeah, it's a very grown-up answer. But the question is, if you would, I mean, you have your tools together. So if you think about your favorite insight, if you would like to make a bet with Marco, so typically it's a bottle of champagne, as we know. Then what would be the kind of neuroscience insight that you would like to tease out? Because you must have something in your mind that you can differentiate with your toolbox, which of course neuroscientists call this a hypothesis, but why probably you have one.
Well, maybe first, I don't have any high level insight on neuroscience because my background is math and computer science, but
that's okay.
Half of my thesis that was mainly on brain imaging data. I would actually say that I believe that optimal transport is here to stay with brain imaging data because it's really important to take into account the folding patterns of the brain. We cannot just pretend to solve the inverse problem without taking into account that geometrical component. And perhaps maybe not necessarily using optimal transport.
I'll be back in a second. I'm sorry. This is home office. It's terrible. Okay, just keep going.
Yeah. So we used optimal transport to model that spatial component, but now I'm seeing that there are other people trying to do convolutional neural nets to model that geometrical part, using some graph knowledge of the brain as well in their convolutional nets, using LSTMs to model the temporal part. So basically, I don't think that, I think that the future of solving inverse problems must take into account that geometrical knowledge of the brain geometry.
I of course fully agree with this. But in
maybe
principle,
maybe this could be the last question. So
yes, I will. Okay. So in principle, what I see in your method that is very interesting from the neuroscience perspective is that you can actually do this, that you can resolve these geometrical issues in the brain. So which means that you can actually find out whether this geometrical knowledge matters or not, and where the difference between the subjects are. So that would be my hypothesis, my impromptu hypothesis.
Yes,
so
we actually tested this when in simulations. For instance, when we solved the inverse problem, we solved the inverse problem with different lead fields and with the same lead field, and we noticed a significant improvement when we use different lead fields in the inverse problem. So using the specific geometry of each subject leads to better source localization. So certainly using geometry helps.
Yeah, thank you. Thank you very much.
Thank you, Klaus. So we move on to the questions of Dirk Lorenz.
Okay, so first also, thank you, a lot for this talk, and also for this very nice thesis. After reading the thesis, I was kind of like feeling like this one here. But then after the talk, it feels a little bit more like that guy here. So it was very inspiring what you told, and I have just a few questions left because the others already asked so many of my questions already. So maybe I start with a technical question, which is about this debiased barycenter algorithm. And probably I was just did not get it from your thesis or presentation, and maybe you said it, but I did not get it. What's the rationale behind it, and why is it debiasing actually? How is this debiasing happening?
First, well, the first intuition is that when you remove the autocorrelation terms, then you have from a technical perspective, you have S of alpha alpha equals 0. So that's the first obvious thing. And perhaps the second thing, if you want some more high-level intuition, when you do optimal transport, you have you have the first OT alpha beta term will be attractive. So that will attract particles to each other when you minimize it. And the other OT alpha alpha and OT beta beta terms will be repulsive. And that repulsion, loosely speaking, will counteract somewhat the entropy blurring that tends to smear the distributions. So yeah, but the important thing that I forgot to mention in the presentation is that this debiasing only happens when you're using a ground metric such that the kernel, so its exponential, is a positive definite matrix. So that's crucial to have these properties. It's not for any cost metrics. Yeah.
Okay, thanks. Another question is a little bit more on the modeling side. Is so you introduced this dynamic time warping to align the time series, and I was wondering why is this a good idea, and why is this better than just using a fixed time shift? So if you use a fixed time shift, and what I thought was if you use dynamic time warping, you would allow that one signal increases much faster after time warping than it used to be, and wouldn't that kind of disturb the signal too much in contrast to just shifting it by a constant time shift?
I don't understand what do you mean by use a fixed time, like infer a time shift and then translate everybody so as to agree?
Yeah, somewhat more like this. So not distorting the time, but just shifting the time.
Yeah, you could. There are basically the usual thing in with MG data. You would first try to align in the sensor space. So you'd have your time series first, and you would try to align them, and then you try to solve the inverse problem. There are a lot of methods that propose to use dynamic time warping to do that. But I think, as you said, dynamic time warping is not just for self-dynamic time warping captures both dilatations in space and time shifts. So we would like to capture both actually. And if one subject, for instance, goes up too fast, at the end it doesn't really matter, because you would always align it with the second largest peak. So it would increase the cost, but intuitively I don't have any intuition on how it would impact the barycenter though. I'm not sure if it would gain, its distance would be larger, so certainly it would have more impact on the barycenter. So perhaps it would attract the barycenter towards it. So
okay, and then I have one practical question, and probably you also answered this in the thesis, but I missed it. So at least if you go to unbalanced transport, but also if you do these barycenters, you have a lot of ways to choose. For example, for the unbalanced thing, there was this weight gamma. So how did you do it? Because I think it should affect the results a lot.
You mean, yeah, I mean the parameter to fix the marginal penalty?
Yeah, for example, the gamma. I think it was called gamma in your presentation.
For that, in the beginning, we had just a heuristic. So in practice, you can notice that gamma needs to be to be scaled proportionally to the ground metric. So basically, if you set gamma to the largest value of the ground metric, then you would pretty much guarantee the most transported mass. Basically, if gamma is too low, you transport nothing because you have no marginal constraints. You just pi equals 0. And as you increase gamma, you you start imposing conservation of mass, and you transport stuff. So when if gamma is set to the largest value of the ground metric, then basically it's like you are saying that you are ready to pay the largest cost possible to transport 1 unit of mass.
Okay.
So that's basically an intuition that you can see from numerical experiments, and just using the Gaussians now with the closed forms, you can see this exactly in the expression of the closed form. You can see that gamma is actually needs to be for Gaussians. It acts opposite to the difference between the means of the distributions. So if the means of the distributions are far from each other, then you need to increase gamma to force transportations, to force the transportation. And the different, if you take for instance just Dirac distributions, and you want the maximum possible transportation, you need the difference of the means will be just the largest value of the ground metric. So we need to set gamma proportional to that difference.
Okay.
In practice, we just we set it to around 80%, or I think I'm not sure exactly, but we set it to a high percentage of the ground metric values in order to guarantee mass transportation.
Okay, I see. Yeah, sounds reasonable. Then I have one final question, which is more an open question, I guess. And because you know so much about this optimal transport and epsilon regularization by entropy, do you know anything about how to estimate the distance of the planes of the optimal one, unregularized, and the regularized one, and how to measure the distance? And so of course one converges to the other in some sense, but how? Do you know anything about this error estimates, or in different metric or something?
You mean estimating the transportation plan?
The difference of the plans, unregularized and regularized ones, so the blurred ones to the non-blurred ones.
You want the plan, the matrix?
Yeah, the plan, actually the plans, right?
Well, you can always compute it with Syncore. I don't understand the
Okay. My interest would be, could you, as if you have chosen an epsilon like that, and then you calculate this plan, can you tell me how far it is away from the optimal plan in some way, from the unregularized optimal plan?
If you let so for instance, if you just compute the entropic optimal transport plan, I'm not sure I have the convergence rates in mind, but under some guarantees you have convergence towards the unregularized one, and you can see that in the Gaussian case as well. So, but I'm not sure. I don't have the actual convergence rates in mind.
Yeah. Okay. Thanks. I think this was my questions. Thank you.
Okay. Thank you. Now the last examiner. So Julie. Julie Delon.
Yes, do you hear me?
Yes.
Yes, okay. So thank you, Hicham, for your presentation. It was really clear. And a good complement to your manuscripts. So I wanted to say before asking questions that I was really impressed by your work. It's really impressive. You have both strong theoretical results and beautiful and convincing applications. So congratulations for this. I have a few, so all my questions have already been asked by the other members of the jury, so well, I still have a few questions. So my first questions would be, probably very naive because I know nothing about neuroimaging. But still, so from what I understand, you in everything that you do, you have a fixed grid, fixed support. That's why it's so convenient to use regularized transport, optimal transport, and your ground cost is the length of the geodesic on the cortical surface, right? So my first question, so it has probably been asked already, but it's how important is this cost? Is this choice of the cost? And would it be interesting to consider other costs than this one?
Yeah, so we actually used a distance on the mesh of the brain, basically using.
You mean a 3D distance on the mesh?
No, we used. That's a possibility, but then you wouldn't be taking into account the folding patterns of the brain. So we actually used the geodesic on the surface, yes, and approximated with the triangulated mesh. I don't see. Well, it would be perhaps simpler to use a 3D ground metric. Perhaps that would be the case if you were trying to infer sources in the volumic space of it, like in the entire brain. But since here we are focused just on surfacic solutions, we have sources that reside in the superficial layer of the cortex. So it makes more sense to use a ground metric that takes into account the geodesic surface. But yeah, you can always use another ground metric. But I don't think you would get the same detail in your barycenters.
But okay, so the cost is really the length on the surface. Yeah. It's not the length to the square or something else.
It's the length of the shortest path between two edges of the graph.
Okay. Okay. Okay, and similar question. So you have a fixed grid for all subjects. So is it traditional to use a fixed grid in this kind of experiments, or would it be interesting to do the same kind of things with different grids? And okay, so the first part of the question is this. And I ask the second part after.
Yeah, that's a good question, because with if you really want to use optimal transport in more proper way from a theory perspective, you would use it you would model your data as real signed measures with positions and weights, and then you optimize both positions and weights. That from a computational perspective would be heavy, but using the fixed geometry comes from the fact that you have an inverse problem, and your matrix X in your inverse problem, the design matrix, is fixed. So the design matrix basically tells you if you have an electrical current at this position, what is the magnetic field that you would measure outside the head at multiple locations. And if you want to do this with free supports, then you would need to compute that design matrix on the fly at each iteration as your sources move in the brain. So that's that must be taken into account. And second thing is that it's not as far as I know, I don't think it's easy to constrain the sources to be on a complicated surface. So at the end, you would still need a model for the surface if you want to stay in the surface, or to maybe to find ways to project the sources out and on and to this and back to the surface. So it comes with challenging problems as well.
Yeah, I was thinking about, but I don't know if it makes sense for this neuroimaging application. But I was thinking about different grids for different individuals. So so different graphs, and using some kind of Gromov-Wasserstein or something like this to be less dependent on the matching between the direct matching between the graphs. I don't know if it makes sense for your application. Well, it also answers. I know there have been questions about what do you do when you have when you have distributions on different dimensions. For instance, one in 3D and one in 2D, and Gromov is one of the possible answers. So, but I don't know. It's much more costly. So.
Yeah, I don't. Yeah, especially if you want to use hundreds and hundreds of subjects. But well, I think with like to go with your idea, the first thing we should probably do is use a specific ground metric for each subject, because so far we assume that everybody is aligned to the same brain. So we are actually using a template brain, which is the average surface of the subject, so an average grid, and we compute the ground metric on that grid. And but the design matrices are different. So the design matrices are different across subjects, and their columns are aligned with the template. So the first thing that we could do to take more geometrical properties into account is to have a ground metric that is specific to each subject. And we can still compute barycenters with a set of ground metrics. The problem that we had with that is that as we increase subjects, we have more ground matrices that we need to store. So it's not a scalable approach.
Okay. Second naive question on the neuroimaging part is at first you have a whitening process at the beginning. And this whitening process is different for each individual?
Sorry?
The whitening step, it is different for each individual?
Yes.
And how, because for this whitening process, you have to estimate a matrix. And how reliable is it? And how important is it for the following?
That part I didn't really explore that much, but basically you need an estimator of the covariance matrix, and we use a regularized estimator of the covariance matrix. And if I remember correctly, I think it's revolve estimator that we use to estimate the covariance matrix, but that's pretty much all I know about the whitening step.
Okay. A few questions about the entropic optimal transport chapter. So first, so I really like this chapter. Those are beautiful results. So you say, so I completely understand why you worked on this closed form on Gaussians. It's really beautiful, and it was great. It was really great to read this chapter. So you know how you can use it to quantify how well you do when you use regularized entropic optimal transport. So my question is, do you have other use or application in mind when you do that, or it's because at some point in your chapter you say you suggest that it's also interesting to have these results on Gaussians for application. I mean that, for instance, we know that the Burst-Wasserstein distance is used a lot for, or the Gaussian map is used a lot for applications for texture in imaging, for texture interpolation or something like that. So would you advise to use the entropic map that you computed for such applications or for other applications?
Yes, we have. for instance, you could use it if you're approximating your distributions anyway using Gaussians. And I reviewed the paper last year that used the Beer-Wasserstein as an approximate. They actually used Sinkhorn, but at the end they ended up estimating a covariance and a mean, and used an approximation using Beer. So you could use the closed form instead to be exact. The other thing in applications that I have in mind, well, perhaps basically as a way to compare different stochastic algorithms to see how well you are doing, to compare different algorithms to compute entropic OT. And as a theoretical tool to validate results that you find, and to measure how much you are, whether you can do better or not, for instance.
Okay. Okay. Yeah, the result is true for singular matrices, because you suggest that it is, but yes.
Well, yeah, the proof relies on the fact that Gaussians have densities. So the matrices should not be singular for the proof to work. But the formulas that we obtain, we can write them in such a way that they can be valid even for singular matrices. So
okay, so you asymptotically it will be true also for singular matrices.
I think so, yes.
Approximate them. Okay. Okay. I had a question about elliptic distribution, but I saw in your manuscript that you answered already this question, so I removed this one. And a last obvious question from me, because I worked a bit on optimal transport between Gaussian mixture models. So is it would it be interesting to?
Yeah, I actually tried for a few weeks to generalize that to Gaussian mixtures, but it's not an easy thing to do, because if you just try to do the same idea in Sinkhorn,
I agree.
You cannot integrate ugly inverse.
I tried also, but it didn't work. Okay. Okay.
It would be a good idea to maybe if you have if you can use this Gaussian closed form, if you have, for instance, a Gaussian mixture, maybe we could find a way, even if an approximate way, to identify the components of the mixtures and find just try to understand how optimal transport occurs for Gaussian mixtures, and maybe then we can like divide and conquer and use the closed form to match the Gaussians. But I don't think it would be. I think it would only be an approximation. I'm not.
I agree. Okay, I don't have any more scientific questions, but I wanted to ask you, in your manuscript, there is a joke at some point about the London Zoo.
Yes, that was.
What is the link between the London Zoo and optimal transport?
So that was mentioned also in the report of Stefan Hoff, and yeah. So the story behind it was that I was tired and writing, and and the BBC was playing on the TV, and because I was tired, I just started typing what I was hearing. So.
Okay. That was a good laugh. So thank you again.
Okay. Well, thank you, Julie. So maybe before giving the floor to the PhD advisors, I will ask myself a few questions. So before asking questions, a comment on, as everybody, I read the thesis and looked at the presentation. I really liked it. It's a very nice combination of topics. It's always treated in a way that I find elegant. And I learned a lot of things, especially about entropic optimal transport. So for instance, I realized only in your PhD the importance of choosing the underlying distribution with respect to which you compute the entropy that actually matters computationally. Okay, so I have a few questions. Can you hear me?
Yeah.
Okay, yeah, okay. Julie was freezing in front of me, so okay. So in your PhD, you use Wasserstein barycenters a lot, and there was a question about the presence of outliers. So I wondered, did you think about using medians instead of barycenters? And do you know why there is a very strong emphasis in the optimal transport community on barycenters and almost nothing on medians? Do you have an idea why? And do you think it could be useful to?
Yeah, that's a good question. I've actually never thought of it before. I would perhaps argue that maybe the interest towards barycenters is motivated by an optimizer viewpoint, that it's easier perhaps to compute. But that the robustness question is certainly a major limitation of the use of optimal transport in our model, and we have to find a way to address it. But I'm not aware of any directions towards computing medians with optimal transport.
Okay. Because from an optimization point of view, you could just take a sum of not squared Wasserstein distance, just plain Wasserstein distance, and then. But probably a few things would like algorithmically, I imagine.
But that would mean since we use the entropic, that would mean you would have square roots of the entropic OT. Yeah, I have no intuition, but.
So the idea was maybe the only idea in mind would be to use iteratively weighted least square, something like that. It might be related to things you already do, actually. Another question is about the time warping chapter. Actually, I found it very nice and very elegant, but there is something that puzzles me, is that it's if beta is equal to 0, it's completely free to reparameterize in a monotonic way. But in practice, wouldn't it make more sense to take a minimization over all possible parameterization, which are monotonic, and then maybe penalize, I don't know, the Lipschitz constant of the parameterization, or of some integral of a differential like a LP norm of a differential of the parameterization, something that forbids large variations of your parameterizations. Wouldn't it make more sense in practice rather than saying it's completely free to, well, not completely, but quite free to move mass or to move the time a lot?
Yeah, so for beta, we had some small theoretical guarantees that control the temporal sensitivity, but I'm not sure I understand your idea. So we want to make an automatic choice of beta driven from the data?
Not really. It's more in the formulation of the dynamic time warping. Instead of just asking for your time warp to be monotone, mm-hmm. You want it to be to control some, let's say, LP norm of its derivatives or something like that. You know, you don't want time warping to be too wild, and this is something that you could impose instead of having this beta. Or, but maybe computationally it's not tractable. I don't know. I wondered whether, well.
Yeah, that's a good idea. I think it should be explored. Well, in practice, we didn't have enough. We didn't have really issues with setting beta, so we didn't really think of going in that direction.
Okay, and the last, maybe more technical question. It's about the reweighted iterative Bregman projection for computing deconvolved barycenters. Mm-hmm. So this is a non-convex optimization problem, and you mentioned that you use some DC techniques that come from a paper of Gasso and co-authors. So I wonder what kind of guarantees do you have in this setting? Do you converge to global minimizers? Do you converge to fixed?
Yeah, you converge to a local minimizer.
And is it not a problem when you use it in your pipeline with automatic differentiation and so on?
Actually, I haven't really used that algorithm much because, well, it was just basically I had to find the algorithm to solve that problem, just to illustrate the fact that when you use the product measure as a reference, you have a shrinking in your barycenter. And we just had to find an algorithm just to compute the Gaussian and to visualize the shrinking. But it's true that, well, with retrospect now, I realize that, yeah, it should be clearly stated that this barycenter, well, the thing is, the thing is, the barycenter problem is a convex problem.
Mm-hmm.
It's a convex problem, but to solve it, I write it as a difference of convex functions. And the tricky part is that I want to use synchron. I want to use synchron. So, and to use synchron, I linearize the minus log to the log to do that.
Mm-hmm.
So, the algorithm converges to a local minimizer, but it's a global minimizer for the entire problem. So there shouldn't be any problem with that.
Okay. Because it's a non-convex formulation of a convex problem. This is what you said. Okay. Okay. Well, I think that's it for me. So maybe I give the floor to Alexandre and Marco. So I let you decide who starts.
Marco, you raise your hand, so you want to speak first?
Yeah, I think you should maybe close because Hicham was hosted at INRIA, so I think it's your turn to talk last, somewhat. I think it would be fair. I mean, although I feel I have been very implicated in Hicham's PhD thesis, of course, throughout the 3 years, and so this gives me a way to start. So I just wanted to say, of course, as a supervisor, I was super impressed throughout those 3 years. I mean, there's several times where Hicham bluffed me by his curiosity. I was just commenting a bit with Klaus on the chat. It's impressive for me to see how Hicham has grown from a student. So I remember we started doing an internship about now 4 years ago, and you could detect really very nice writing skills in Hicham. He was very, very careful about details, about writing some memoirs, and this really stood out if you would compare it to other students in his class. But then what I was really, really bluffed by is by Hicham's ability to constantly ask questions on his own. You know, for instance, the debiased synchron barycenters was a project that completely came out of his mind. I personally do not really care about biasing and smearing in barycenters, but this is something that really Hicham thought was actually important, and actually Hicham convinced me that actually this was a blind spot, and indeed that this was a nice solution. And so now for the anecdote, I am in this situation where I'm actually implementing his algorithm, because I've recently launched a toolbox on optimal transport. So here it's a funny situation where the professor implements the algorithm of the student, and so I will have a few comments to share with Hicham about some of the recent works also. So I really wanted to congratulate Hicham for all this work. He's also Hicham has been putting in a lot of passion and time into all of those papers. So maybe I can just. There's two things I just wanted to mention more on the research side now that I've really said all of the nice things. So one comment is this came up twice in the presentation. This is the idea of so Klaus mentioned it, Quentin mentioned it, and I just wanted to pay justice to some people who have done a bit of robust fast-Einstein barycenters. And so there is a paper by Eustacio del Barrio, who's been studying this idea of having robust K barycenters, but the paper is mostly applied to barycenters of Gaussians. So it's this idea of trying to discard some outliers when computing barycenters, but the algorithm is essentially for Gaussians. So I think it would be interesting, of course, question to explore this with more arbitrary barycenters. And the other question I had is, so this is also goes to a question that Julie asked. So you mentioned that you were always using the shortest path metric on the mesh, on the cortex mesh. So if I go back to a few years when we started chatting about those ideas with Alex, this was a bit frustrating, but we were finding that the nice results that we got were for exponents p, that were slightly above 1 and not just for p equals 1. And so I remember that when we were chatting with Gabriel, and maybe this is a question Filippo might have asked, it's known that Wasserstein 1 barycenters are very degenerate. So here you're using both entropy, and I was wondering whether you had explored a bit playing with exponents that were slightly bigger than 1.
Yes. So with brain imaging applications, we noticed that the barycenter works better with p equals 1. Oddly enough, compared to all the other applications where p equals 2 work better for images and other things. So I think it's probably due to the fact that when you compute, the mesh is not regular. Maybe it has something to do with that. The fact that your triangulated mesh is not regular, and but mainly in the performance of the inverse problem did not differ that much. Just the visual rendering of the barycenter. So varying p from 1 to 2 did not really impact the performance in general of the inverse problem.
Okay, so I just wanted to let you comment on that. So again, thank you very much, Hicham, for those. So three great years working with you as a collaborator. I really enjoyed it from the beginning until the end. Thank you very much.
So I will take over. So first, I would like to also thank Hicham for all the positive vibes he had on the lab, and basically basically inspiring also people around him. He's a very passionate student, curious about many things, and sometimes curiosity can be more like a bug than a feature. But I think for Hicham, he's still always very focused. When he has a curiosity, it goes deep, and it keeps, I would say, hitting on the thing until it really cracks it. And I think he really has a huge potential for research, and I hope that he will continue in this path. The other thing I could say is that so Hicham is very creative and like I would say in French, un personnage. I don't know how to translate this in English, but just to give a few anecdotes that I mean, you could see Hicham basically lying on the floor with his feet up, trying to look and stare at the board for I don't know how long, and just until he really gets the idea that he's missing. And so it was a bit, I would say, funny for the other students to find Hicham basically in this situation in the lab, and so I think it created a lot of fun, but in the positive sense for everyone. And it was always so great to see someone passionate like Hicham for his work. And I think his work was very interdisciplinary. He really took I would say, bit the bullet of going to doing real data processing for neuroscience. And I don't know if you can realize how much effort it takes to go from real data to, I would say, publication-ready papers with figures that you would put in neuroscience papers. There's a lot of engineering that you had to master to be able to do this. And at the same time, he really, I mean, went deep in the math when he had to, and when he felt very often looking at the data that there was something weird or something to be understood. And so when I told him when something is unexpected, just try to understand why. There's probably something to understand. And I think it created all the interesting questions that he asked himself by looking at the data, by making some experiment and reading the proofs and basically questioning things that needed to be questioned. So I'm very happy to see this, I would say, hopefully positive ending of this defense. I'm also very sad to see Hicham leave. Yes, that's pretty much it. And thank you, Hicham, again.
Thank you very much.
Okay, so this is the end of this defense. So we will now gather the jury and probably come back here to give the result and maybe congratulate Hicham. Is it the plan?
Let's do this. I don't know if Hicham, we need you to open the other room. I will ping you on Mattermost if we need you to start the other room. Okay, otherwise, Hicham, you stay here,
yeah.
And we'll come back here afterwards.
Yes.
So I probably missed it. So how do I get to the other room? Did I get a link already, or?
Yes, the second link is in the first email.
Okay.
So yeah, I need to open the second. I'm not sure I can choose on that.
No, I'm away.
Let me. Hi, Stefan.
Hi, the passcode didn't work, but I guess.
Yeah, can you just stay here for a moment? I will leave this meeting, but I'm not sure I can open the other Zoom without closing the stream.
Okay, I'm just trying to link now.
Yeah. I think I need to close this meeting.
Salut Hicham, sur l'autre réunion, on nous dit qu'on ne peut pas se connecter parce que...
Je sais, oui. En fait, le problème, c'est que il faut que j'arrête celui-là. Du coup, il faut que j'arrête. Je vais arrêter le stream, je pense. Bon, j'arrête le stream et je vais lancer et je lance l'autre Zoom.
Ok, désolé. Ciao, ciao.